Sorry, I ran out of space. So let me start the proof again. I'm saying that if we have this non-homogeneous differential equation and the homogeneous version, which is the same as the non-homogeneous except I changed the right-hand side to 0, and we have one solution yp of the non-homogeneous differential equation, and we have a basis of the homogeneous differential equation. This is a dimension n space, so here's a basis of n solutions. Then all solutions of the non-homogeneous differential equation are that one particular solution of NH plus all possible linear combinations of the basis of solutions of H. So the reason this works is that all solutions, let's say U, of the non-homogeneous differential equation satisfy, I'm going to plug in U minus the particular solution to the left-hand side of NH. So the nth derivative of that plus a1 of x times the n minus first derivative of that, etc., plus a n of x times u minus yp equals, I guess I could write that up here, plus a n of x u minus yp equals, so basically have the left hand side with u substituted in for y. So nth derivative of u plus a1 of x n minus first derivative of u, etc., up to a n of x u. And then I've got yp plugged in with a minus sign. So minus nth derivative of yp plus a1 of x n minus first derivative of yp, etc., up to a n of x y p. Now if u satisfies that equation, then this should be equal to f of x. But yp satisfies that differential equation, that's equal to f of x. So that's equal to f of x minus f of x, which is 0. So that means that u minus yp is a solution of the homogeneous differential equation, because this whole expression is equal to 0. So it's a solution of H. So that means that we can write u minus yp as some linear combination of the basis elements of the homogeneous solution space. So that means that any solution u we want to the NH can be written as yp plus this linear combination. So every solution of the non-homogeneous system of equations can be expressed as one solution plus all possible solutions of the homogeneous differential equation. Let's do an example of that. So for example, let's ask, is y equals 1/2 e to the 7x a solution of y double prime minus y prime minus 6y equals 18 e to the 7x. So this is the left-hand side of the homogeneous differential equation we looked at before, and I just added a right-hand side. So let's ask, is that a solution? And if so, what are all solutions? All right, checking to see that it's a solution is pretty easy. So the solution is 1/2 e to the 7x. So y prime is 7/2 e to the 7x, and y double prime equals 49/2 e to the 7x. And then if we plug those in on the left-hand side, let me call this equation NH. This is non-homogeneous because the right-hand side is not 0. So the left-hand side of our non-homogeneous equation is second derivative, 49/2 e to the 7x, minus first derivative, minus 7/2 e to the 7x, minus 6 times the function, minus 6 times 6/2 e to the 7x, which is, let's see, 49 minus 13 is 36. 36/2 e to the 7x, which equals 18 e to the 7x, which equals the right-hand side. So yes, y equals 1/2 e to the 7x is a solution of the non-homogeneous differential equation. Y double prime minus y prime minus 6y equals 18 e to the 7x. Now we know a basis of the solution space of the homogeneous system, y double prime minus y prime minus 6y equals 0, because we looked at that before. And that is e to the negative 2x and e to the 3x. So thus, all solutions of NH, which I just erased, y double prime minus y prime minus 6y equals 18 e to the 7x, are this one particular solution, y equals 1/2 e to the 7x plus all possible linear combinations of e to the negative 2x and e to the 3x. So c1 e to the negative 2x plus c2 e to the 3x, where c1 and c2 are real numbers. The end.